So let me just repeat that since I just started the recording. I just wanted to say that this will probably be the last lecture on stabilizer error correction. We'll probably have another lecture or so on the next step, which is fault tolerance. And after next week, I mean, certainly next week, I may take 2 lectures to wrap up error correction as such. And then we'll start doing quantum Shannon theory from the last week of March. Okay. So we'll have about 10 lectures on quantum Shannon theory. Okay. So we have discussed various aspects of the stabilizer formalism as such. And yesterday we discussed the idea of stabilizer codes, right? So today we are going to talk about the error correction aspects, which we have so far not really discussed. We've only discussed examples. So the idea today is to complete the picture and discuss conditions for error correction using the stabilizer formalism. Okay. So we have these 2 objects to deal with. So S is basically an abelian subgroup of the n-qubit Pauli group. Pn, and associated with this is a vector space, which is basically the vector subspace spanned by states. So these are, remember now, these are n-qubit states such that S psi is a +1 eigenstate of S. So it's equal to psi for all S belonging to this stabilizer group S. And well, the code space, basically I'm defining it as the span of all these states, right? And we have seen various properties of this, including the dimensionality aspect. So that's the last thing I did yesterday, where I showed that if I have basically, so if S has R generators, then the dimension of the code space C associated with it is basically n minus r, 2 to the n minus r. So it's 2 to the n by 2 to the r, 2 to the n minus r, which is what we call 2 to the k, where k is defined to be n minus r. So if I have a stabilizer group with r generators, then that essentially gives me what is called an NKD code, right? It gives me an NKD quantum error correcting code, right? Where k qubits can be encoded into n qubits, and d, I've already defined this sort of, is the distance of the code, right? And d is often written as 2t plus 1, right? Where the code can correct for errors on up to t qubits. Okay, so this seems a somewhat indirect way to define the error correction properties of a code, right? Why don't we directly define it with t rather than defining it with d? So today we'll give some physical meaning to this d as well by first talking about error detection and then about error correction. Okay, and these are very related notions, as we'll see. So the first thing I want to talk about is error detecting properties of a stabilizer code. Okay. So now we'll have to recall a few things. So what is the set of errors that we are dealing with? Remember that we are now talking about general purpose codes where we will break down any error model in terms of Pauli errors. So as far as we are concerned, the set of errors is simply the same as the set of n-qubit Pauli operators, right? So this is simply Pn, it's a group, right? The set of errors is essentially the Pauli group. Why? Because the errors that we are going to correct for are either of the X, Y, Z type, or if there is no error, it's identity. And then we are simply going to make n-fold tensor products of these, right? So if I have an operator x1, x2, etc. with identity everywhere else, I3, I4, etc., In, then this is a 2-qubit X error, right? It's an X error on the first and the second qubit, right? And so on and so forth. So all our errors are essentially going to be of this form. They're going to be tensor product of Pauli errors. So this is a 2-qubit X error, right? So the question one is asking is, what subset of these Pauli errors can a particular stabilizer code detect? So first I want to talk about detection because that comes naturally with stabilizers, right? So note that the set of errors we are going to be talking about is essentially this Pn, which is the Pauli group on n qubits. So the error correction or error detection properties of a stabilizer code obviously relies on properties of the Pauli group. So this is the first thing to note. The second thing to note is that every pair of Pauli operators either commutes or anti-commute. If I'm just talking about single qubit Paulis, then there's nothing that commutes with anything except, of course, identity. But because X, Y, and Z anti-commute. I hope everyone remembers what anti-commutation means. It simply means XZ plus ZX is 0. Of course, commutation is the negative sign. But once you start making tensor products of Paulis, then you can see that, for example, X1, X2 will commute with Z1, Z2, right? But X1, X2 will anti-commute with Z2, Z3. Right? So I go and the rest of the qubits all have identities, right? So this is just to note that every pair of operators inside this big Pauli group are either going to commute or anti-commute. And this then immediately gives us the desired error correcting or error detecting property. So the third concept to note is a very important concept. So the stabilizer group is a subgroup of the n-qubit Pauli group. Associated with this, we can define the group or the subgroup of all operators in Pn that commute with the operators in S, that commute with the elements of S. So this group in group theory language is defined to be the normalizer of the subgroup S. This is just terminology from group theory. So this is in fact how the normalizer is defined, and it will be denoted as N of S. So let's just write this down formally. N of S is simply the set of all operators belonging to the larger group, of which both of these are subgroups, such that, so let me call these as E actually, not S. For me, S is a stabilizer operator, an operator inside the stabilizer group. So the set of all E operators E such that ES is SE for all operators S belonging to the stabilizer. So we are essentially viewing now the n-qubit Pauli group via two subgroups, right? One is the stabilizer group and the other is the normalizer group. But are these two groups distinct or will they have an overlap?
They can have an overlap, right?
Yes, good. Indeed, they will have an overlap because this group is an abelian subgroup, right? So it has a bunch of commuting operators, right? They are all mutually commuting Paulis. Now, if I pick some element of this, some S, and say what is the set of all operators that commute with S, obviously some of them will be sitting inside the stabilizer itself, right? So the normalizer will be a larger group, right? And it will indeed have overlap with the stabilizer group, right? In fact, not just will it have some overlap, it will include the operators in the stabilizer group, right? Because if I think of all the operators in the larger Pauli group that commute with every operator in S, of course, it includes the operators in the stabilizer as well, and a whole bunch of other operators from this larger group, right? So it turns out that you can now very easily state the error detection condition. So I said I want to first talk about conditions for error detection. So the first statement is that all operators in the normalizer minus, so all operators that are in the normalizer but not in the stabilizer are undetectable errors. And the second statement is that all Pauli operators in this n-qubit Pauli group that do not belong to n of S are the detectable errors. So this is basically the set minus symbol, right? So let's just prove this immediately and then we'll understand the statements as we prove them. So let some E belong to this normalizer. Now, there are two possibilities. Either E belongs to the stabilizer or E belongs to the normalizer minus the stabilizer, right? So either it belongs to the stabilizer itself or it belongs to that part of the normalizer which is outside the stabilizer, like here, right? So if E belongs to the stabilizer, so let me call this A and B, then E acting on any psi in the code space is going to be psi, right? That's how we define the stabilizer, right? So obviously then E is not an error as far as the code space is concerned. Right? It does not affect the states in the code space at all. So E is not an error. It leaves the states in the code space invariant. There's nothing to be done, right? But if E belongs to the part of the normalizer which is not in the stabilizer, right? Then what happens? Look at E of psi, right? And then ask, what is the action of some element of the stabilizer on E of psi, where S is some element of the stabilizer. What happens? You know that SE is the same as ES, right? But ES is the same as E psi, right? I'm sorry, S psi is the same as psi. So ES acting on psi is the same as E psi. And this is true for all psi belonging to the core space, which means what you've shown is that E psi is also a +1 eigenstate of S. And this is true for all operators in the stabilizer, right? Now, E psi also being a +1 eigenstate of S means that there is no measurement that can detect the error E psi, right? So E psi changes the state in some non-trivial way because you cannot show that E psi is the same as psi. If E psi were the same as psi, then E better be sitting inside the stabilizer. So E psi is not equal to psi. So it is some other state phi, right? Which is also a +1 eigenstate of S, but it is not the same as psi. So essentially, you have modified psi to E psi. This operator E has modified the state to E psi, which is some state phi, which cannot be distinguished by any measurement of the operators in the stabilizer. The handle that you have on the code space is only the stabilizer operators, right? You know the operators in the stabilizer, right? So let me state it as no measurement of stabilizers can detect the error E psi, right? So these two states, both being +1 eigenstates of all the operators in the stabilizer, cannot be distinguished by measuring the operators in the stabilizer, right? So these are undetectable errors. On the other hand, if I had the second part of the theorem, which says that all Pauli operators which are in Pn but that do not belong to n of s are detectable errors, that is easy to understand because if E belongs to Pn but outside of the normalizer, then it means that E must anti-commute with all elements of the stabilizer because any pair of Paulis can either commute or anti-commute, right? So since E does not belong to n of s, it must anti-commute. So now we'll ask what is the action of S on E psi. You'll see that this is now minus ES acting on psi. S psi is the same as psi, so this is minus E psi. So now you have E psi is a -1 eigenstate. It's an eigenstate corresponding to eigenvalue -1 for all operators in the stabilizer, right? Now remember that the Paulis have either +1 eigenvalue or -1 eigenvalue, and the eigenstates corresponding to the +1 eigenspace and the -1 eigenspace must be mutually orthogonal. So this means that now the state E psi, which is phi, is actually something that is orthogonal to the code space itself, right? Because the code space is the +1 eigen subspace, right? So it's a +1 eigenspace. So now you have transformed it to something which is a -1 eigenstate. So it is something which is now orthogonal to the code space. So if you recall, we needed to map different errors, which if you wanted to the effect of the error to be detectable, you needed to map the code space to mutually orthogonal subspaces, right? So that is shown here very neatly, that if an operator which is a Pauli which does not commute with the stabilizer, then it must anti-commute. And because it must anti-commute, it means that such an operator will take the state in the code space to something that is orthogonal to the code space, right? And so these are detectable errors. And in fact, the way to detect them is by measuring operators in the stabilizer, right? I'll just call them stabilizers, right? And this is what we repeatedly noted when we were discussing these examples that we knew in terms of the stabilizers, right? So again, let's go back to the examples that we had. So if I look at the 3-qubit bit flip code, I will simply call it the 3-1 code, okay? Because it can only detect X errors, right? So the stabilizers were basically generated by these two operators, right? Z1, Z2, and Z2, Z3, right? So now you realize that the set of detectable errors So what is this set? Basically, operators which are in the 3-qubit Pauli group. So remember that the Pauli group one is talking about now is P3, which anti-commute with these operators. So which are those? So those are indeed operators of the form X1, identity on the other two, X2, X3, right? If I take X1, X2, right? So I hope you realize that this is indeed the set of detectable errors, and they all do not belong to the normalizer of S, right? They do not commute with the stabilizer. So I can deduce this commutative or non-commutativity property just by looking at the generators of the group, right? Because it's an abelian group. So now you look at operators like X1, X2. This is a 2-qubit X error, right? What does it do? Well, it anti-commutes with one of the stabilizer generators, right? But it commutes with the other stabilizer generator. And because of this, you look at what it does to the code words, right? X1, X2 acting on 0, 0, 0 gives me 1, 1, 0, and X1, X2 acting on 1, 1, 1 gives me 0, 0, 1. Now this actually gets confused with X, X3 acting on 0, 0, 0 is also 0, 0, 1, and X3 acting on 1, 1, 1 is 1, 1, 0, right? So both of these end up being the same subspaces. They end up leading to the same set of states as far as the 3-qubit code space is concerned, right? So I could, for example, write down a different set of detectable errors, which might involve only the 2-qubit errors, right? And not talk about the single qubit errors. But if this is my detectable set, then these errors, which commute with the stabilizer generators, but they don't belong to the stabilizer, cannot be distinguished, right? Maybe a more pathological case is actually X1, X2, X3, right? So this, I think, actually conveys what the theorem states there. So if I look at X1, X2, X3, then this is a 3-qubit error. This takes 0, 0, 0 to 1, 1, 1. and it takes 1, 1, 1 to 0, 0, 0. So basically you are within the +1 eigenspace of Z1, Z2 and Z2, Z3. Okay. So just to clarify, strictly speaking, in this case, x1, x2 is not an operator which is which has a definite commutativity or anti-commutativity property with the stabilizer generators. Why? Because you look at its behavior with respect to the two different stabilizer generators, right? It anti-commutes with one and it commutes with the other. Okay, so I should refine my condition slightly and say that, yeah, but I guess, yeah, it's okay for now. Maybe when we do the error correction conditions, it gets refined automatically. Anyway, so I hope this example conveys all the different cases for you. So one is, there is a set of errors which has a distinct commutativity property, right? They definitely do not belong to the normalizer. In fact, they strictly anti-commute with the stabilizer generators. But there are these intermediate operators like x1, x2, which do not have definite commutativity or anti-commutativity property with all the stabilizer generators, right? Because I'm talking about commutativity or anti-commutativity with the entire group, right? So x1, x2 are somewhere outside of this, right? If I split the Pauli group Pn into operators that either commute with S or anti-commute with S, then x1, x2 sits somewhere. x1, x2 doesn't fit into either of these two groups, right? On the other hand, you have something like x1, x2, x3. In this case, it's clear that x1, x2, x3 is actually in the normalizer, right? Because it commutes with both the generators, both Z1, Z2 and Z2, Z3. Okay, so this is an operator which is definitely inside the normalizer, right? And this definitely cannot be corrected for by this code because it has this property that it maps you back. So you see, actually, what it does is it leads you to confuse the logical 0 and the logical 1. And you cannot actually detect this error by any measurement because you're still inside the code space. So no matter what alpha 0L plus beta 1L you prepare, if this error acts, you're going to be sitting inside the code space itself. You will just go to alpha 1L plus beta 0L, right? So such an error is actually called a logical error. I'm just throwing this terminology here. And these are the hardest errors to deal with because you have not even gone outside the code space, but you are in serious trouble because you've confused the 0 and the 1, right? But these are the errors which simply cannot be detected by this code, but these are the errors which can clearly be detected by the code because they belong to, they do not belong to the normalizer. They strictly do not belong to the normalizer of the stabilizer group, right? Okay, so finally, I want to talk about the relationship between distance and detectability, right? And then I'll move on to correction, error correction, okay? So now, how does one define, let's go back to this terminology, right, of this NKD code, right? So the distance D basically implies that the code can detect errors on up to D minus 1 qubits, right? So you are in an n qubit space, so you can have errors on 0 qubits, 1 qubit, etc., all the way up to n, right? And you have encoded k qubits worth of information there. So up to how many errors can you detect, right? So for example, if I talk about Shore's code, which is a 913 code, right? The distance 3 means the code can detect errors on up to 2 qubits, right? The relation between detection and correctability is that the code can correct errors on up to d minus 1 by 2 qubits. So why this difference between detection and correction? Now imagine I have these n qubits, right? 1, 2, 3, etc. n. So it's one thing to be able to say that there has been an error. So let's go back to this example itself, right? So if you notice this x1, x2, then you see that they actually do cause the code words to get mapped to something that is mutually orthogonal to the code words. The 110 is actually orthogonal to this, which means in principle, you can detect these errors, but you can't correct for them. Why is that? Because you don't know whether what happened is a 2 qubit X error or what happened is a single qubit X error, right? So these will in principle be detected, but you can't claim that this code can correct for 2 qubit X errors, because every 2 qubit X error has some overlap with the single qubit X error. If I do X2, X3, then you will notice that it has an overlap with X1 and so on and so forth. We've discussed this before. So that's where the detectability versus correctability comes in, right? So when I say I can detect errors on up to d minus 1 qubits, it means that I can point out that there have been errors on some d minus 1 of these locations. But what is that error and how to reverse it, that may not be possible, right? So detectability and correctability can be slightly different, right? I hope you understand this point, that if I move to something which is distinct from the code space, so if I say that this is my code space C, right? So long as I move to something which is outside of C, then there may be a way to detect it. But there may be different errors which map me to the same place, which is outside the code space, in which case I can't really reverse back because I don't know which of these two pathways happened. So all I can say is there have been errors on so many qubits, right? But I can't really recover from these errors. So one possibility is that sometimes people use what are called just error detecting codes. And I think I gave an example of this in the tutorial with respect to the amplitude damping channel, where you can just throw up your hands and say, I can't really recover the information because I cannot exactly identify the error and reverse for the action. But I know that the state has errors. Okay, so I'm going to discard the state. So often this is used to discard the errored qubits. Another scenario where you can imagine that error detection is useful is, for example, when some qubits have just been erased somehow. And we'll talk about erasure when we talk about the Shannon theory in subsequent weeks. But erasure is another important thing where you may just want to know whether a particular qubit has just changed or not. And if it has changed, I simply throw out that qubit because I can't correct for it, right? If I'm only interested in detection but not correction, it gives me slightly more, right? Because I can detect errors on up to d minus 1 qubits. That's what the distance means. But if I want to correct, then that kind of halves, and we'll actually see this showing up in the condition that I'm going to write down just now for correction, right? But I've already written down the condition for detection, which is simply that the error operator must not belong to the normalizer of the stabilizer, right? And so that's why in principle, the 2 qubit errors are also detectable errors as far as the 3 qubit code is concerned. In a similar way, you can show that the Shor code can also detect errors on 2 qubits. It can also detect the 2-qubit errors, but it can't correct for them, because again, you will confuse between different possible errors. When I say errors on up to 2 qubits, it includes the single qubit errors. But now you can no longer distinguish the single qubit and the 2-qubit errors. So though you may be able to detect the 2-qubit errors, you will not be able to correct for them if you include that in the set of errors to be corrected. Okay, fine. So how does this distance now go back to the stabilizer? So one can actually get the distance of the code simply from looking at the stabilizer properties, and the way to do it is to understand something called the weight of a Pauli operator. So I hope the idea of detection versus correction is clear. So I'm moving to the next idea here as far as stabilizers are concerned. So the weight of a Pauli operator. So the weight of an operator E belonging to Pn. Can everybody still hear me?
Yes,
Ma'am. Okay, fine. Because I'm keep getting messages from WebEx which are disconcerting me. All right. So weight of an operator E which belongs to the n-qubit Pauli is simply defined to be the number of locations in the tensor product. Okay, let me say number of terms actually to be formal. So the number of terms in the tensor product which are not equal to identity. So it's basically the number of non-trivial terms in the tensor product. If I think of E as an error, because I said every operator in Pn is technically an error as far as we are concerned, it's the number of non-trivial locations with a Pauli error. Oh, sorry, the number of locations with a non-trivial Pauli error. Right? By non-trivial, I mean not identity. Right? So remember that you can expand this any n-qubit Pauli in terms of some xi, zi raised to ai, bi, and then it's a tensor product over all of these i's, right? I going from 1 to n, right? This is the kind of tensor product it is. So the weight of this operator is simply the number of locations on which one of ai or bi is not 0. If both ai and bi are 0, then that location is simply identity. So it's basically the number of I such that one or both, right, are not equal to 0, right? So let's just look at some examples. So if I just talk about x1, x2, and then identity everywhere else, then what is the weight of this operator? The weight of this operator is 2. The weight of, for example, x1, x2, x3, x4, x5, x6, and then I7, I8, I9. If I think of the 9-qubit code, remember this is one of the stabilizer generators, right? What is the weight of this operator? The weight of this operator is 6. If I write down an operator like this, x1, z4, and then I could write y8. What is the weight of this operator? It's understood that everywhere else is identity, so the weight of this operator is 3, right? So now what has the distance got to do with weight? Well, it turns out that the distance of the code, this is an important statement. The distance of a stabilizer code S, right, is basically the minimum weight of an operator E belonging to the normalizer but not in the stabilizer. So in other words, it is the smallest weight of an operator that commutes with all S in S but does not belong to S, right? So now if you go back to the 913 code, or even if you look at, let's look at the 913 code, for example. I've said that the distance is 3. So why is this the distance? Well, because this goes back to the error detection condition, right? So the distance, the way we defined it, tells you that you can detect errors on up to d-1 qubits, right? That's how we defined it. So that means that any error operator which has non-trivial Paulis on d-1 qubits must not belong to the normalizer, must not commute with the stabilizer generators, right? So the smallest weight of an operator that belongs to the normalizer must be 1 greater than this. Is that idea clear? So if I say, for example, this, so let me say that this is because any operator that belongs to n of s and minus the stabilizer, right, cannot be detected, right? Cannot be a detectable error. So if one says that errors on up to d-minus qubits can be detected, that means that all Pauli operators with non-trivial Paulis in d-1 locations of that tensor product, they must all anti-commute. So they cannot belong to the normalizer. The smallest operator that belongs to the normalizer must have a weight which is greater than d-1. So the smallest integer that's greater than d-1 is d, right? So that's why the distance d must be the smallest weight of an operator that commutes with the stabilizer and doesn't belong to the stabilizer. So let's just quickly understand this with the 913 code. So recall that the stabilizer group for this code, once again, it suffices to just look at the generators, right? Is Z1, Z2, Z2, Z3, Z4, Z5, Z5, Z6, Z7, Z8, Z8, Z9, and then it has these X1 to X6, and then it has the X4 to X9. So these are all the, okay. So now let's think of any weight 2 Pauli operator, right? So what is the claim? If the claim is that the distance is 3, then it must mean that the smallest weight of a Pauli operator that commutes with the stabilizer must be of weight 3, and that any weight 1 or weight 2 Pauli operator must anti-commute, right? Even if it doesn't anti-commute with the entire stabilizer, it must anti-commute with at least some of the stabilizer elements, right? So if you look at, for example, X1, X2, X3, etc., all the way up to x9, these are all weight 1 Pauli operators, right? So they all anti-commute with what? With all the Z stabilizers, right? With stabilizers of the form Zi, Zi plus 1. Correct? So they anti-commute with all the Z stabilizers. If I look at the single qubit Z errors, they all anti-commute with the X stabilizers. Similarly, with the weight 2 operators, you will find that there is some subset with which they will anti-commute, right? So if I look at x1, x2, for example, then it anti-commutes with Z2, Z3. So it cannot belong to the normalizer, which is the group of all operators that commute with all the operators in the stabilizer. But if I look at weight 3 Paulis, like x1, x2, x3, right? Then this will anti-commute oops, I mean to say that this, so this commutes, if you notice, yeah, so that's what I would say. Sorry. This commutes with Z1, Z2. It commutes with Z2, Z3. And of course, it commutes with the rest of the Z operators because there is no Z in the first 3 locations, right? On the first 3 qubits. They're all Zs on the other qubits. And of course, it commutes with all the X stabilizers. So these are the only non-trivial 2 things that you have to check. And of course, it commutes with all the other stabilizers. I'm using stabilizers and stabilizer generators somewhat interchangeably. I hope you realize that that's because if something commutes or anti-commutes with the generators, then it must, there'll be other elements in the group with which it will commute, with which that property will carry through, right? Fine. So if it commutes with all the generators, then it commutes with the entire group. So that means that this kind of an operator is something that belongs to the normalizer. And in fact, you can show that this is the smallest weight Pauli operator that belongs to the normalizer and does not belong to the stabilizer, right? Because, so of course you can talk about things like Z1, Z2, right? If I look at weight 2 Paulis, you may ask, well, what about the operator Z1, Z2, right? That's also a weight 2 Pauli. And this, of course, must commute with all the elements in the stabilizer because it is a part of the stabilizer itself. It is one of the stabilizer generators. So this is not an error, right? So there are also these weight 2 operators, right? Which commute with everything in the stabilizer. It commutes with x1, x2, etc. up to x6. That is one of the stabilizers. And the other stabilizer is the other one, x4 to x9. Remember, the 3 qubit x's are not stabilizers. They don't leave all the code words invariant, right? It's only the 6 qubit x's which are the stabilizers. Okay, so we've now seen all aspects of this. There are operators like this which belong to the normalizer, but they also belong to the stabilizer. So these are not even errors. So the smallest weight of an operator that belongs to the normalizer but doesn't belong to the stabilizer is a weight 3 operator. And that is why we say that the Shor code has distance 3. It can detect errors on up to 2 qubits, but it can correct only single qubit errors. So let's now come to the correction part. So I have basically what this lecture is doing is it's tying up the different notions. We earlier saw detectability and correctability purely from the code space and the code word point of view. Now one is able to do all of this simply by looking at the stabilizer generators. So once I have the stabilizer generators, I know what is the normalizer. Immediately I know which are the operators which belong to the normalizer. I can identify that. First of all, I can identify operators that don't belong to the normalizer. So I can identify the detectable errors, and immediately I can also identify the errors which cannot be detected. And then I know what is the distance of the code, right? Up to how many qubits can it detect errors on? Okay, right. So the last part, I have another 15 minutes, is to talk about error correction conditions for stabilizer codes. Questions? Okay, so this shouldn't take us too long because we've discussed all these properties already. So again, we will simply state this in terms of whether certain operators belong to the normalizer or don't belong to the normalizer. And then we will relate that back to the algebraic error correction condition, which we derived a couple of weeks ago, right? So let me state this formally. So let S be the stabilizer for a code C of S. Then suppose I have some set of error operators EI in Pn such that, now you see where that half factor comes from. You have to now look not just at whether the error commutes or anti-commutes with the operators in the stabilizer, you have to look at this overlap, right? If you remember, the error correction condition was written in terms of the overlap, right? So similarly, you have to now look at the overlap operator and say that, suppose the set is such that, so let me write J and K here, that for every pair of J and K in this set, EJ dagger EK, remember this is a product of Pauli, so this is also a Pauli, right? It does not belong to the normalizer minus the stabilizer for all J and K in the set, right? In the set. For all EJ, EK in the set EI. Then this set becomes a correctable set. For the code that is associated with the stabilizer. Okay, so it should be relatively easy to prove this, right? So start here. So the arguments are the same, right? So given this operator EJ dagger EK, what are the possibilities? It can either belong to the n-qubit Pauli group outside of the normalizer, right? The normalizer is a set of all operators that commute with the stabilizer, right? Or it can belong to the stabilizer itself, right? In which case it is not an error. But we are not interested in EJ dagger EK. Remember, we have to go back to the EI itself. So let me not note that here. Or it can belong to this. So let us start by saying, so this is a statement, right, which says that if these operators are such that EJ dagger EK does not belong to this, then this set is correctable. So let us start with that premise. So let EJ dagger EK not belong to the normalizer minus the stabilizer, which means one of these two possibilities holds, right? So in which case, let's say that this is A or this is B. So let us look at B. If it belongs to the stabilizer itself, then Ej dagger Ek acting on any state psi is equal to psi for all psi in the code space. Oops. So this, I hope you see, will immediately give us the error correction condition. It will satisfy the error correction condition because if P is the projector on the code space, then what this means is Ej dagger EKP is the same as P, or in other words, P Ej dagger EKP is some constant which is nothing but 1 times P. So this implies that the QEC conditions are satisfied, right? Because remember, the QEC conditions say that P Ej dagger Ek must be some alpha Jk times P. It's just that the alpha Jk is just 1 in this case, right? So directly you can see that the QEC conditions are satisfied very trivially. The other option is that Ej dagger Ek belongs to the larger Pauli group outside of the normalizer. So it belongs to Pn minus the normalizer of S, right? In that case, it anti-commutes with the elements of the stabilizer, right? So in that case, well, remember, we let's be careful about this. We looked at operators like that x1, x2. They don't anti-commute with all the operators in the stabilizer. They commute with some of the operators in the stabilizer, but they anti-commute with some other operators in the stabilizer. So they must, so when I say something is outside the normalizer, it means that there must be at least one generator of the stabilizer. So there exists some GL, let me call it, or some G naught or something inside the stabilizer. So some generator of the stabilizer such that, actually I can just call it G. Okay, okay, I think I need to write down all the generators. So let me call it G1. Okay, so there exists some stabilizer generator which I call G1 such that this operator must anti-commute with G1. Once again, note that if something does not belong to the normalizer, it doesn't mean that it anti-commutes with every operator in the stabilizer. It means there is at least one operator, and in particular, you can, without loss of generality, say there must be one stabilizer generator with which this operator anti-commutes. So now we want to know what is P, Ej, dagger, EKP, right? Because this will then give us back the error correction condition. So you want to know if this satisfies the error correction condition. So let us now write down the code space projector in terms of the stabilizer generator. And we did this exercise yesterday. Recall that the code space projector P on C is the product of the projectors onto the +1 eigenspaces of the stabilizer generators. Right? So P is nothing but the product of P1 plus P2 plus etc. PR plus, right? Suppose there are some R generators. In this case, it's an NKD code, so you will have some number. So which means that P is of the form identity plus GI by 2, right? This is how you project onto the +1 eigenspace corresponding to the generator GI, right? So, yeah. So now you have the product of all of this over I going from 1 to, let's say, n minus k. So let's say that it's an NKD code, right? Then you will have n minus k generators. So this is a product of the projectors onto all the +1 eigenspaces, right? And so it should be 2 to the n minus k if it comes out, but I put it inside the product. Okay, so now what is EJ dagger EKP? Well, this is now EJ dagger EK times. So remember, I called, there is one generator with which this operator anti-commutes. I called that as G1. So let me write that out first. And then it's a product over all the remaining I going from 2 to n minus k, I plus gi by 2. Okay. Why am I writing it separately? Because the EJ dagger EK anti-commutes with this. So this now becomes identity. I hope you see that this becomes identity. So rather, okay, let me say EJ dagger EK plus EJ dagger EK times G1 becomes minus G1 EJ dagger EK by 2, right? Because it anti-commutes. That's what we've assumed, right? There must be one generator with which it anti-commutes, and we've said let that generator be G1. So then you have this remaining product again. So now I'm going to take the EJ dagger EK to the other side. So it's I minus G1 by 2. And then you have this full product. So what am I going to do now? I'm going to sandwich this with a projector on this side as well, right? So now I want to know what is P EJ dagger EKP. So taking off from here, so this was what? This was EJ dagger EK times P, right? And P can be expanded in terms of product of +1 eigen projectors. But because it anti-commutes to the first one, that actually becomes a minus projector. And I hope you can see that it actually becomes orthogonal. So if I now do P EJ dagger EKP, this becomes P times identity minus G1 by 2, EJ dagger EK, and whatever the rest of it, right? Now this P will again have an identity plus G1 by 2, right? This P will again have an identity plus G1 by 2. It will have various other products, but I can move things around with plus or minus signs. So I will eventually end up with an identity plus G1 by 2 and an identity minus G1 by 2. And then there will be a bunch of things, right? And this will be 0 because P times identity minus G1 by 2. Remember, P is the product of all +1 eigenspaces. It's a projector onto all the +1 eigenspaces. This is a projector onto the -1 eigenspace of G1, right? So when I take the product of projectors belonging to different eigenvalues, obviously they must be mutually orthogonal. So this must be 0 because this will have something like I plus G1 times I minus G1, and then you can see that this is nothing but I minus G1 squared, which is 0, right? So all of this leads up to the fact that when I take P EJ dagger EKP, for any operator EJ dagger EK, which does not belong to the normalizer, right? So rather which belongs to the Pauli minus the normalizer. So it belongs to the n-qubit Pauli group minus the normalizer. So not belonging to normalizer means doesn't belong to the stabilizer as well. but rather it belongs to the larger Pauli group minus the normalizer. So once again, you see the QEC conditions are satisfied, right? By what? The QEC conditions are satisfied by the individual EI operators, right? In fact, the QEC conditions are satisfied directly in the orthogonal form, right? By the set EI. In fact, it is already in the so-called orthogonal form, right? Which means that it already tells you that the error acting on K will be orthogonal to, the error EK will be orthogonal to the error EJ, right? And so they will be detectable and correctable because you can distinguish. So the fact that the right hand side is actually 0 means that these errors are actually distinguishable, right? So it actually satisfies the error correction condition in the orthogonal form. So let me say that EJ and EK can actually be distinguished. Okay. All right. So I think that pretty much proves the statement of this theorem that if I have a set of error operators such that EI, the adjoint times this, and of course these are all Pauli's, so EJ dagger is the same as EJ, it doesn't matter. It just means that the product of two different Pauli's in the set EI does not belong to the normalizer, rather it belongs, so let me just draw a picture here finally. So there is the big Pauli group. Inside that Pauli group, you have the stabilizer, which is some little abelian subgroup of this Pauli group. And then there is the larger group, which is the normalizer, right? Which contains the stabilizer, but then has a whole bunch of operators which are not in the stabilizer. So these are really the problematic characters out there. These are errors that can neither be detected nor corrected. Then in the larger Pauli group, there are operators which can be detected, and then there are errors which can be corrected, right? So any operator which belongs to this Pauli group but does not belong to the normalizer can be detected, but any set of errors which are such that the product of two of these error operators belongs to the Pauli but doesn't belong to the normalizer, any such set can be corrected for, right? Can not only be detected, but can be corrected for. Okay. So I think, let me just stop here today. And I think this pretty much concludes the discussion of stabilizer error correction. There are a few other interesting points to be mentioned about stabilizers, and I'll do that in Monday's class. But whatever I have taught until now will be what you'll be tested on in your mid-sem. Okay. Questions? Okay, there are no questions. Then good luck for your mid-sem, and I'll see you on Monday.